Here we're decomposing some tensor products of Sn irreps. So gamma lambda and gamma mu are both irreps of Sn. And we look at this tensor product, gamma lambda tensor gamma mu, and we ask how many times, when we write these as a direct sum of irreps, how many times does it contain the trivial representation, gamma s, because it's generated by the symmetrizer, and how many times does it contain this other one-dimensional representation, the sign representation, called it gamma a, because it's generated by this anti-symmetrizer a. Before we determine these multiplicities, let's observe that the characters for the symmetric group are all real. So why is that? P inverse is in the same conjugacy class as P. Why is that? They have the same cycle structure. You can just invert the cycles, the disjoint cycles individually. So the cycle structure of the inverse is necessarily the same as the cycle structure of the element. And this means if they are in the same conjugacy class, they have the same characters. So the character of P is the same as the character of P inverse. But for a unitary representation, the character of P inverse would be just the character of P complex conjugate. And for a non-unitary representation, we know that there is a unitary representation which it is equivalent to. And the characters of equivalent representations are the same. So we always have this property here for the symmetric group, that the character and the complex conjugate of the character are identical, so they are real. Now let's calculate these multiplicities. So we have gamma lambda tensor gamma mu, and then there's gamma s. The trivial representation might show up as some multiplicity as, and lots of other terms. And we want to calculate the as. So how do we do this? We do this using characters. 1 over n factorial, order of the group, sum over all group elements. And now we need the character of the representation for the multiplicity we are looking after. So chi s of P complex conjugate. Complex conjugation doesn't matter, as we know. And then we have here the character for this product representation, lambda tensor mu. This one here is 1. It's the trivial representation. So we're left with just 2 characters in the sum, and then we can use character orthogonality. So we have here sum over all group elements. The character of the tensor product is just the product of the characters. It's something we observed earlier. So we have chi lambda of P times chi mu of P. And if we like, we can write a complex conjugation here, because it doesn't matter anyway. So we really see that we can use character orthogonality now. This sum is 1 if the 2 representations are equivalent, and it's 0 if they are not. So we really get 1 if gamma lambda and gamma mu are equivalent, and we get 0 if not. Okay, and this 1 here is now just, or the 0 is just the multiplicity of the trivial representation in this tensor product here. And we can essentially repeat this calculation now in this next case, where we are after the multiplicity of the sign representation. So gamma lambda tensor gamma mu, that's AA, the multiplicity of the sign representation, and some other terms we don't care about. So what is AA? Again, 1 over the order of the group and factorial, sum over all group elements. Now we need the character of this sign representation here, and then again the character of the tensor product. And the character of the sign representation is just the sign. It's a one-dimensional representation, so representation matrix and character are the same. So we sum over all group elements, and we have the sign of the representation here. Complex conjugation doesn't matter, this is also real. And here we have chi lambda of p times chi mu of p. And if we like, we can write an irrelevant complex conjugation here. Everything is real anyway. But the point is that this product here, that's just the character of the associate representation of gamma lambda. Because we get the associate representation by multiplying a representation with this sign, and then the sign just multiplies all the characters. So now, same argument as before, character orthogonality. We have 1 here if this time gamma lambda tilde and gamma mu are equivalent. And that's just rephrasing that gamma lambda and gamma mu are associate. And it's 0 if they are not. And that's exactly what the theorem up here stated.